We're going to consider briefly floating stability. I'm not going to spend too much time on this. It's a mathematically very challenging concept to really work out, but conceptually fairly simple and important that you understand it. Naval architects spend a lot of time worrying about floating stability. If you go into that field, you'll have to learn a lot more about it. So here's what the basic problem is, the basic challenge. Every boat is going to have a center of gravity. So consider again our rectangular boat here. Imagine that it's long in and out of the page. So we're looking at a cross section of the boat. It's rectangular. So it's got some width to it here, and it sinks into the water to some depth, d. And then it's going to have a center of gravity. And the center of gravity is just based on the boat, assuming the boat has sort of a uniform weight distribution inside it. The center of gravity will be at the volumetric center of the boat. If it's a hollow metal shell, like many boats are, center of gravity might be right in the middle, just as I've drawn it. And then there's also a center of buoyancy. A center of buoyancy is the place where the buoyant force acts, on the boat. And that's going to be the volumetric center of the region that is submerged, as long as that region contains a fluid of uniform density. So again, typical to one of our boats, it might be full of just air. That air is basically uniform in density. So we can estimate that the center of buoyancy is going to be sitting here, right here, in the center of the region that is submerged under the water. So the region that is air that is actually under the water level. So that's our center of buoyancy. When the thing's floating nice and calmly, these two are lined up perfectly. mg, of course, acting downward on the center, through the center of mass on the boat, and buoyant force acting upward through the center of buoyancy. And those will balance each other so that FB equals mg, and the boat will just sit there. But of course, the boat could tilt. If the boat tilts, that's going to move the center of mass and the center of buoyancy relative to each other. So if we draw the boat now, I'm looking more like this. It's now tilted. And the question is that tilt going to cause the boat to capsize, or is it going to right itself? So in order to see what's going to happen, we're going to put the center of mass back. Now the center of mass hasn't moved relative to the structure. It's simply still right in the center of the boat. So that's still position G. But the center of buoyancy is the volumetric center of the region that is under the water. And you can see from this picture, a lot more of the boat is underwater over here than is over here. So that center of buoyancy is going to have moved over here somewhat. So maybe it'll be here. You can see from that picture, now the center of mass is still mg, pointing straight down due to gravity, but the buoyancy force is now pointing upward this way, pushing upward this way, FB. Same amount of the boat is going to be submerged. The magnitude of the buoyancy force is not going to change, but the position of its effective application has changed. It's shifted out here to the left. And that's going to cause the boat to rotate back this way, as you can see. The way the net moment is going to be acting, that is going to cause a shift that causes the buoyant force to shift left, and that's going to push the boat back to its equilibrium upright position. So this picture as drawn suggests that this boat, as I've drawn it, would be stable in this configuration, that it would, if it gets tilted, the center of buoyancy moves to the left, the center of gravity kind of stays where it is, and that's going to tend to push the boat back upright where it came from. But we can draw a different boat and see that that is not always what happens. So if you consider a different boat of a slightly different shape, still a rectangular shape, here's my water, but now my boat is tall and kind of skinny. So my boat's going to be tall and skinny. Here's my water, it's coming in here. Here's my center of gravity right in the center of my boat. Now you know what's going to happen. You've seen boats like this, or they're not really called boats. They're called things that flip over. But this would be your center of buoyancy now, right? Because that's in the center, the volumetric center of the region that's under the water, and this is going to be the center of gravity. If we tip this boat like this, we see that the volumetric center of gravity is here, and the volumetric center of buoyancy is here, roughly. So the buoyancy force is acting up, the gravity force is acting down, and that's going to cause it to rotate that way. So it's going to end up, of course, right on its side. It's going to flip over to its side, where it's going to achieve this situation, where the gravitational center is going to be here, the buoyancy center is going to be just below it, and now we're basically both back to the boat that we had on the first thing I drew. So we can see that basically this is how buoyancy works. As I say, the exact calculations for this are quite complicated, but it is important when considering floating objects to think about not only whether they will float, that is whether they're positively buoyant or sinking or neutrally buoyant, but also whether they would actually be stable in the position they're in. And that depends on the position of the center of gravity relative to the center of buoyancy when they tilt.